countdown has been going smoothly overnight. We have not been working any technical issues since the tanking began at 11:09 last night. Loading the Space Shuttle external tank with the 525,000 gallons of liquid hydrogen and liquid oxygen was concluded at 2:05 this morning. Once again, all our countdown events are proceeding normally, leading to an opening of the launch window at 8:06. We're cautiously optimistic about the weather. We're now at the astronaut quarters in the operations and checkout building at the Kennedy Space Center, where the STS-59 cake is in the center of the table. Mission specialist Linda Godwin down at the end of the table, and sitting next to her, mission specialist Jay Apt. Linda Godwin and Jay Apt working on the Space Radar Laboratory during the flight. And next to Jay Apt is mission specialist Tom Jones, who will also be flying on the Space Shuttle once again in August on the next Space Radar Laboratory mission, SRL-2, again on Endeavour. Our pilot Kevin Chilton, and sitting next to him is our commander Sid Gutierrez, and then on the far end is mission specialist Rich Clifford. This is shuttle launch control at T-minus 3 hours and counting. The countdown has picked up once again for the launch of STS-59 and Endeavour, and all of our activities are on schedule this morning. We're cautiously optimistic about the weather. The broken layer at the shuttle landing facility is expected to go scattered sometime after sunrise, so we're still hopeful that if the wind does not become any stronger than it is currently, that we will have a launch this morning. Among the tools that the ICE team is using is the portable infrared scanner. That's the most important device, which obtains temperature measurements on the surface of the vehicle, and can also spot any leaks. And they're looking for any ice which could be on the tank or other areas of the fixed service structure, which at launch could break off and strike the orbiter. This is shuttle launch control at T-minus 3 hours and holding. Our commander Sid Gutierrez, outfitted there with his communications hood. And final fit check of the helmet. And our pilot Kevin Chilton. He flew previously on the STS-49 mission. He's ready to go this morning. And there's our payload commander, Linda Godwin. And mission specialist Rich Clifford. Tom Jones, mission specialist, who will be flying again on Endeavour in August on SRL-2. astronaut Dave Leesma there talking with Jay Apt. This is shuttle launch control at T-minus 2 hours, 51 minutes and counting. Our commander Sid Gutierrez, followed by mission specialist Tom Jones. There's Jay Apt, Linda Godwin, Rich Clifford, Dave Leesma, and Hoot Gibson also riding down the elevator. He'll be flying the shuttle training aircraft this morning and the T-38 for weather reconnaissance. Mike Stevens from NASA Security, greeting the crew as they come out.
Round two.
And they'll leave Gibson off all the way to the pads. And away they go. Find it quite pleasant out at the pad this morning. The temperature is 72 degrees with winds out of the east-southeast at about 10 to 15 knots. Aboard Endeavour, helping the crew again today, is astronaut Andy Thomas. He's been in the crew compartment configuring the switches, making any changes necessary to the compartment, and will be assisting the astronauts as they board.
Endeavour CDO, reach loud and clear. TLT loud and clear. MS1 loud and clear. MS2 loud and clear. MS3 loud and clear. MS4 loud and clear. ECL, your step 828.
For step 828, cabin press is reading 14.85.
Copy that. That's steps 826 through 832. And CDR, you can go ahead and reconfigure BFS memory.
Roger.
And CDR OTC, go to close cabin vent valve.
Roger.
This is NTD taking a launch status check. Say go, no go for launch. OTC, go. TBC.
TBC's go.
TTC. TTC's go. LPS. LPS is go. Houston flight.
Go.
Mala.
Mala's go.
STM. STM's go. Safety console. Safety is go. SP. SP NTD.
Go ahead, NTD's SP.
Go, no go for launch.
Go.
CDR.
Endeavour crew is go for launch.
LRD. LRD is go. And SRO.
SRO is go. You have a range clear to launch.
Copy. Endeavour OTC. Close and lock your visors. Maintain O2 flow. And Viaton Dios.
Roger, thanks a lot, Mark. And we'll see you in about 10 days.
Copy that.
T-minus 45 seconds, standing by for the handoff to Endeavour's onboard computers in about 10 seconds at T-minus 31.
TLS is go for auto sequence start.
Endeavour's computers now controlling.
25. 20. 15.
Sound suppression water system being activated.
10. TLS is go for main engine start.
7, 6, main engine start. 5, 4, 3, 2, 1, Zero and liftoff of the Space Shuttle Endeavour, observing the changes of planet Earth.
Roger, roll, Endeavour. Houston now controlling, Endeavour rolling on course for 57 degree inclination, 120 nautical mile orbit. Endeavour already traveling about 300 miles an hour on a course that will have it go northeast above the Atlantic Ocean, parallel to the eastern seaboard of the United States. Endeavour speed now 1,000 miles an hour, 5 miles downrange.
Endeavour, go at throttle up.
Roger, go at throttle up.
Altitude 9 miles. 3 engines now back at full throttle. 1.5 minutes since launch, Endeavour's already burned more than 2.25 million pounds of propellant and weighs less than half of what it did at liftoff. Altitude now 15 miles. Speed 2,100 miles an hour, 15 miles east of the launch pad. Flight controller standing by for burnout and jettison of the twin solid rockets. Good solid rocket booster separation confirmed. Endeavour now 33 miles northeast of the launch pad, altitude 30 miles, speed 2,700 miles an hour.
Endeavour, performance nominal.
Copy, performance nominal. T0, SRB ignition.
Liftoff confirmed.
Copy.
Full program, Houston.
Roger, roll, Endeavour. Flight guidance, see the roll.
Copy.
Throttle up, 3 at 104.
Endeavour, go at throttle up.
Roger, go at throttle up.
Endeavour Houston, we see a nominal MECO, ohms 1 not required. You have a go for the ET photo DTO.
Roger, that's in work.
Flight Capcom.
Go ahead, Capcom.
I'd like to get the AOS and LOS times for Diego worked up to add to the spiel I'll give him for LOS and AOS from the east and the west.
Stand by, Taco.
And Taco, stand by one on the note for Chile. I want to know, do you want me to select an item 17 there in line with stars 29 and 22 as they are in the table, or you want me to clear the table and get them again?
Roger, we're checking.
Flight GNC.
plastic than it does to the rubber. That sounds like another PhD subject.
So this shows on gray. Look on the TV.
Is there any doubt?
Same thing.
And we've got a good picture, Rich.
Okay, Bill, what you're seeing is some live cells growing in the space tissue loss B experiment. STLB, along with its companion STLA, are growing live cells in the microgravity environment to evaluate the effects of microgravity on the growth process. The novelty of STLB is it's making its maiden flight to check out a new video microscope system, which is going to allow real-time monitoring of the cell growth process in microgravity. To check out the system, fish eggs are being used to watch the development of the embryo during early division stages. This is going to evaluate if changes in gravitational force have an effect on cell movement in 3 dimensions. Experiments like this should provide unique insights on the effects of physical forces on cell movement and may provide clues to the understanding of how wounds and organs develop. Okay, Nancy, we'll turn it over to Sid.
Sid Gutierrez, commander of this SRL mission, and this morning I'm going to try to do my most difficult task of the entire mission, and that is to attempt to explain zero Doppler steering. During the course of this mission, we've been initiating approximately 460 maneuvers. In fact, this morning, we just initiated the 262nd of over 460 maneuvers. By the time we finish this flight, we will have initiated more maneuvers than any other shuttle mission. These maneuvers are very important because they help us point our radar in a very special way. In our normal attitude, we fly around the Earth with either our nose forward or our tail forward with the payload bay radar pointed at selected sites. We produce a radar image by sending a radar signal which is bounced off the Earth and returned to an antenna in the payload bay. Scientists use very powerful computers and very complex software to process this radar data in a very special way to produce what we call a synthetic aperture radar image. In fact, just this morning, they transmitted up to us on our TIPS machine a picture of a radar image that was taken of the Galapagos Islands, just yesterday. Probably hard to see this on the television image, but this was created with the radar image. This very complex processing assumes
that the orbiter is parallel to its ground track as it travels around the Earth. You can see that for an Earth that does not rotate, an Earth that's perfectly still, this is probably true. But we all know that our Earth rotates. So as the orbiter goes around the Earth and the Earth rotates, that means that our ground track and the orbiter are not perfectly aligned. And I've exaggerated this a little bit for demonstration purposes. We can make them aligned by constantly maneuvering at just a fraction of a degree per minute, so that as we fly around the Earth and as the Earth rotates underneath us, our orbiter is always aligned with the ground track that we trace across the ground, which is what is really important for the radar. We call this zero Doppler steering.
And this is one of the types of consumables that sometimes can limit flight duration. We, of course, have plenty stored for our mission. And they're very large filters that fit in, that are inside some protective covering that we have to remove before we put them down into the air purification system. And this is done at the end of each of our shifts, the red shift and the blue shift. So we swap out sometimes one and sometimes two cans twice a day. And as this is removed, we very carefully save the tape we're peeling off and the covering, and we put the used cans back in that and store them back in the same area. And sometimes we know that we can come back and get some of those out again if for some reason we need some additional purification capability.
Hi, I'm Sid Gutierrez, commander of the Space Shuttle Endeavour. This message was recorded in April as we were orbiting the planet, studying the surface of the Earth and the atmosphere above it. As we image the surface of the Earth with our radar and visual photography, we've noticed certain rectangular patterns all over the world. More and more of these patterns are appearing in the United States. On closer examination, we realize that these are soccer fields. More people are playing soccer than any other sport, and for the first time in history, the World Cup is being held in the United States. So from way up here to all the participating countries back on Earth, welcome to World Cup. Good luck, but watch out. We're even working on a team up here.
Rich! You let it in! Score!
More head bounce.
There's the
a little more bouncy off.
How about elbows?
Come back down. Remember, it's going to always ricochet off something. A closed volume.
W5RRR, this is N5REX. I'm receiving loud and clear. You know, it's exciting and all to be up here in the shuttle. There's no denying it. And the views are just beautiful. But the thing that really makes you feel good is to know that all those people that worked so hard, so long to make this work, is coming together for them. That really makes, brings a tear to your eye. It's such a happy feeling, isn't it?
At Houston Endeavour, for those watching Sid, he's talking to the Boy Scouts of America down in Richardson, Texas at this time on our shuttle amateur radio experiment, basically a ham radio, and answering questions that the Scouts have lined up for him.
And I don't know if you can see over this far, but here's the visual function tester gear that Sid and I are doing once a day. And I hope I'm on the test.
Oh, can I just go on the ground? No, I'm in the seat this.
And thanks, Jay, we copied in. We will have TV for approximately 7 more minutes.
Now the seat moving on you, Tom?
Yeah.
Does the seat extend over
Well,
to the
maybe
VFT?
the back.
Yeah, the seat should be firm now.
Oh, I'm sorry, Sid.
Oh, I'm real
Yeah, it just slipped back. I need to move it up.
Oh, you need to move forward?
Let's slip back. It's just all this force that's being applied.
Put your body where you want it.
Right, I am.
Right there?
Yeah.
How's that?
Okay.
Good morning to everyone back there on the Central Time Zone. I'm Tom Jones, Mission Specialist aboard the Space Shuttle Endeavour. We're now over the South Pacific Ocean, just southeast of New Zealand. I want to take a few minutes out of our busy schedule up here of maneuvers and science operations to tell you about our studies of global change on this mission. This mission of the Space Radar Lab aboard STS-59 on Endeavour is part of NASA's mission to planet Earth, which is a comprehensive program using the space shuttle and unmanned satellites to study the Earth as the next century begins and to understand the changes that are going on, both natural and man-made. Now, I'd like to tell you about our experiences here for the first 4 days of the flight. We've been seeing traces of both man-made and natural change. Spring is coming to the northern hemisphere. We can see the snow line retreating across Asia, and we're seeing vegetation patterns, land use changes, natural changes caused by weather and geology, like volcanoes and earthquakes. We're looking for all those kinds of phenomena. I'd like to tell you about why we're able to study global change from the space shuttle on this flight. First of all, I want to mention our vantage point up here in orbit above the Earth, what the Space Radar Lab out in the payload bay is looking for, and then give you some examples of the kinds of change that we're hoping to study on the flight. Now, our vantage point here aboard Endeavour is very important. We're about 138 nautical miles above the Earth's surface, circling the globe once about every 89 minutes. And that elevation, that altitude, gives us a horizon that's out several hundred miles from wherever we happen to be over the Earth. And that gives us the broad perspective and the ability for our sensors in the cargo bay to see a long distance and measure change in a reasonably efficient amount of time. Also, because we're in orbit, our speed is very important. Circling the Earth at 17,000 miles an hour, we're able to use our speed to let our radar out in the cargo bay, Circe XR, create a much larger electronic antenna than would otherwise be possible. We can see finer detail on the ground because of our speed across the Earth's surface. That whole technique is called synthetic aperture radar. And also, with our pollution sensor called MAPS in the cargo bay, our speed permits us to cover the world as it rotates beneath us, and thus we can create in just 2 or 3 days a global map of carbon monoxide, a tracer gas of pollution or burning on the planet's surface. So the vantage point here is very important. Now, what kinds of changes can we see from this vantage point in low Earth orbit? Our synthetic aperture radar creates images, pictures of the ground using microwaves, which can be taken during darkness or through clouds. The MAPS carbon monoxide sensor creates a map of global pollution. It traces sources of combustion and how that trace gas, CO, spreads across the globe. Now, using those images and that pollution map, we can look at Earth's past, present, and its future. We can look back into Earth's past by noting changes in the geology of the Earth that tell us about the world's past climate. We can look at the present and take a snapshot, a baseline measurement, if you will, of the pulse of Earth's forests, cities, our production of pollution in both hemispheres, and we can also measure the ecology, the environment, and take its present temperature, if you will. And now we can look into Earth's future by flying the Space Radar Lab twice this year on STS-68 later in the year, and later a radar of this type and a similar suite of instruments could be orbited on an unmanned platform. And by measuring Earth's environment over months and years, we can see the trends on our ecosphere that would help us manage the planet in a better and more careful way.
Okay, Nancy, what we did was earlier today we recorded us doing what we're here for, which is to do a large number of maneuvers to point the radar exactly at the targets that the radar folks are interested in. And we understand from the radar people that they're getting accuracies that are far beyond their initial expectations, and the targets are showing up right in the middle of their radar swaths, and we're real happy to be able to help them do that. Here we are putting in one of the 460-some maneuvers that the ground has planned for us, and it's a real pleasure to be able to go do that and see the results like the radar folks have been showing people down there, and know that we're able to point the orbiter extremely precisely to get very specific targets within range of the radar beams from all of the equipment out in the payload bay. This is what we spend most of our time doing, and what I think you guys have been really helping us check.
We're just now coming upon Chile after passing across the coastline. And the target area for this observation is the Andes Mountains, Central Cordillera area. Dr. Isaacs is mapping the topography and studying the climate in the Central Andes Mountains. He's mapping things such as plate tectonics, or the movement of the Earth's crust in this area, as well as mudslides and other climatic events. This image is of Sicily. This is a real-time image seen exactly as the radar system aboard Endeavour records it. And now Endeavour's radar is crossing the coast of Italy. This is the most southern tip of Italy here. The Matera, Italy calibration site is located in a very flat agricultural area. And the wavy lines in the image are the former Yugoslavian territory, Eastern Europe.
Well, this is a view from one of the off-payload bank cameras showing the radar and zooming out from the cockpit over to the Earth. This is on a pass we did earlier today over Central Europe. You can see the KU band antenna lit up there, and that's how a lot of the data that you're seeing real-time down on Earth gets down there.
Okay, Jody, we're over. We're getting close to the water here in the Labrador Sea.
Okay,
So it looks pretty clear today.
great. We're all listening.
We're seeing some clear areas out there and some sea ice, and there's some sun glare chasing just ahead of us on the sea ice. The Chile's trying to shoot right now.
Okay, we're seeing the XR come down and see the ice looking as large flows that are breaking up.
That's exactly right. There's some very large sections and then kind of wavy-looking pieces where we can see clear water in between.
We see those right now. The leads are showing up quite clearly.
We have a video that we'll show you next, which is a view of the Earth along the across Canada, and you'll see both the Earth as viewed by the astronauts through a video downlink and the Earth as viewed by the radar. And this is coming across the screen now. You see the white areas on the right are frozen lakes. In the radar image they appear black, and the bright areas in the radar image on the left are forests. This is a time of year when thawing is occurring, and in the early part of the mission the astronauts were calling down that all of these lakes appeared nearly completely frozen, and now today they're calling down that some of the ice is starting to break up, and so we're pretty excited about this. This means that we might capture the thaw in these high boreal forest regions.
This is a real-time image coming down from the synthetic aperture radar. The site that is currently being tracked is of the Netherlands region of Flavoland. The orbiter's again moving to the southeast. This is a calibration site of high interest primarily because of its it was artificially created by the Dutch, and it allows for easy interpretation of the radar data once it's obtained here on the ground.
These are the German Alps showing up now on the radar. Now we're approaching the super site at Oberpfaffenhofen, Germany, where the 24 locations with their active radar calibrators are set up. And the Munich airport passing right below. Oberpfaffenhofen is just outside Munich. And the Danube River now in the picture.
before sunrise on the California coast, but the radar can see through that as the California coastline comes into view. On a northeasterly track, Endeavour will cross the coastal ranges, which are mountains that are made from various fault lines. Should also cross over the San Andreas Fault just before the San Joaquin Valley, which is coming into view, a large agricultural area. The orbiter is now crossing the Sierra Nevada to the Mammoth Mountain area, which is a backup super site, which is on the eastern part of the Sierras. As mentioned, this is a hydrology site. The interest here is for the snow cover and the amount of snow cover in that area because of the production of water that the Sierras produce for the Southern California area.
What you're going to see in a minute is a Circe L-band image of Death Valley. Death Valley is one of what we call our super sites. In front of you, you can see the Long Valley, which is the dark area at the center of the image, and on either side you can see the high ranges. Now, a lot of you may be familiar, we produced some similar videos for the Magellan mission. We start out here in the Cotton Ball Basin. The bright, rough surfaces that you see are salt deposits along the bottom of the valley, and also some of the rougher, rockier surfaces. Now, this is L-band, which means that the bright surfaces that you see are produced by sort of rubble-sized or medium-sized blocks. Now we're flying down through Death Valley. The smooth deposits you're seeing are some of the relatively smooth salt deposits on the floor and some of the smoother fans. Now these fans that are coming down from the sides of the valley are produced by much wetter periods in history. What we're trying to understand here at Death Valley with this radar data is what can these alluvial fans tell us about the past climate history of the Earth.
And the coastline coming into view, vision from the synthetic aperture radar as Endeavour crosses the coastline of North America up just above the state of Washington. The data take is of the Juan de Fuca Strait, which is off the coastline, and this is an oceanographic data take for the radar system. Again, designed to observe surface and internal waves as well as wind motion at the sea surface.
We're using 14 cameras on this flight. 35mm cameras, Hasselblad cameras, TV cameras out in the payload bay, a movie camera, and this big 4x5-inch camera.
All right, now this just short clip here is far northeastern Asia on the mainland passing out to sea. And you can see on the video here the coastline of Sakhalin Island, and it's very snowy still in this part of the world as winter ends. And there is some sea ice all along the island of Sakhalin up through the Sea of Okhotsk that the radar is imaging for experiments on the penetration of the radar into the ice field. And you can see some frozen lakes and ponds in the tundra region up here. And in particular, one of the calibration sites for the radar mission to evaluate the performance of the radar beam, its strength and signal intensity, and its and the ability to aim the radar accurately is Sarabetsu, Japan. And that calibration site is coming into view right here. You can see some of the snow-capped peaks around this area of the coast, and then the street pattern there just to the northeast of Sarabetsu on the coast of Hokkaido. And there you see us passing out over the east coast of Hokkaido into the Pacific Ocean.
It's a site that's of a lot of interest to a lot of people because this is a area of the Aral Sea that used to be the fourth largest body of water in the world and is now shrinking tremendously due to taking the water for agricultural irrigation of the cotton fields down in Kazakhstan. And in fact, the area just to the top of your screen there, I'm sorry, to the bottom of your screen, has a number of fishing boats that are left high and dry 30 or 40 miles from the water. Used to be an enormous commercial fishing area, but now it's drying up, and there are predictions that if things continue at the current rate of diverting the water, the whole Aral Sea will be dry by the year 2020.
This is Mission Control. These views are from Endeavour's payload bay cameras as it flies down across the southern Pacific Ocean. On this orbit, it will pass just slightly north of the tip of New Zealand.
Endeavour is on a southeasterly track now out over the Atlantic Ocean just after crossing over the coastline of the east coast of the United States. The orbiter is in a nose-forward position with the payload bay of the orbiter pointed toward Earth.
Endeavour Houston, we're live on the flight deck. Endeavour Houston, New York City sure was impressive.
We're enjoying it too, Mac.
Yeah, Bill, we just got a beautiful pass up the Hudson River and saw West Point.
Yeah, Rich, I'm trying to tell Brent he should have gotten here just a couple minutes ago and maybe seen that other school further down the coast.
Endeavour SRL, no response, but your go for tape change on recorder 3.
Yep. I was able to hot wire around that night.
So does anybody have any spare cell towers?
Yeah, I do.
Would not be used, Tom?
Yeah, I have a surplus.
Okay, I like it.
What a deal. See, I didn't get to see this last time.
That's true.
Daylight insurance. Oh.
This is impressive.
This is a wonderful country.
Breaking at 8 down to 50 knots. 35 knots, easing off. Right on the center line, buddy. 20 knots. 10. Wheel stop. We'd be home.
All right! Way to go, guys.
That was beautiful.
Good job.
Woo! Damn straight. That was good. How'd it feel, bud?
Felt good, a little fast.
It was fantastic.
Right. It felt smooth to me.
Houston Endeavor, wheel stop.
Endeavor is about to get onto the heading alignment circle and will begin executing a 285-degree left overhead turn to align the vehicle for a landing on Edwards runway 22. At about 57,000 feet. Traveling at 875 miles an hour, descending at about 300 feet per second. Now below 30,000 feet, 530 miles an hour.
Endeavor on energy at the 180.
Copy, on energy at the 180.
Endeavor, you're on glide slope on center line, surface wind 360, 2 peak 4.
Roger. Houston Endeavor, wheel stop.
Roger, wheel stop, Endeavor. Sid, your radar laboratory has provided an unprecedented view of our planet, and you and your crew have been a joy to work with. Welcome home.
Thanks.
Fido, still on glide slope and center line?
Yes, sir.
Copy.
Endeavour, you're on glide slope on center line, surface wind 360, 2 peak 4.
Roger.
Copy.